Okay, so welcome to the lecture on the recycling of steel and circular economy. I thought of doing something on waste electrical and electronic equipments, but I would maybe add another lecture to that and then add also on lithium battery recycling, which is, let's say, a hot topic because it cuts nicely into the legislation and policy module. But do not worry, I will not ask you too many questions in the exams from the metallurgical part, but I add a lot of metallurgical part to these lectures so that it's for your own curiosity to understand the science behind it. But the other parts of the lecture are, of course, important. I chose to present on steel. I could have gone with aluminum or something else, but I think steel is a very important topic, and it's the one which has the most impact in terms of emissions. So let's deal with the thing which has the most impact, and let's see how significant steel is and what contributes to the uh, circular economy of steel, and how recycling can play a very important role. And also let's see how recycling may not be enough at all. So we will see all these things together. So the lecture structure is like this. First, we'll discuss the salience, the importance of steel, and then we'll go a little bit deeper into the emissions related to steel, the various part of the steel making process and the emissions that are related to it. And then let's come back to steel recycling and circular economy, how these things can be connected. And I'll tell you a little bit about how steel is recycled, the chemistry of it. It's fun, so listen with an open mind, and let's talk about the very important issue of tramp elements. And I want to introduce you to something else. Steel is recycled historically a lot. We have, let's say, very mature recycling processes that have been developed to recycle steel. But those things may not be still enough to curb the emissions. Okay, so let's say to think out of the box, to have radical solutions in terms of producing steel would also be necessary. I'll take you through two of the very important, let's say, game changers which are being proposed right now in terms of its chemistry in and cutting down the emissions. Of course, they are not going to be asked in exams, don't worry, but for you to know these things exist would be very interesting, just to be curious about what is happening in the field of research. Okay, so this is something that I have already told you in the last lecture. We have an interesting rise of steel production over the years. It has kept increasing. This is a complicated picture. It looks easy now. I'll come back to it later in the slide, but take a good look at the dips. These usually are years of financial crisis. So on the right, you have the Sankey diagram. The fact that I want to emphasize again is see how much of steel is going into the construction industries. More than half of it goes into the construction industries, right? So you have the issue of residence time. It's almost 35 years or more where these steels stay in these buildings. And this relates to a lot of topics that we are going to bring back in this lecture. The residency time, how much the steel stays inside these buildings and structures, and how soon or how delayed the release of scrap will be from these buildings, and will it be enough to satisfy, let's say, a closed loop circular economy of steel. So we'll come back to all these questions, very interesting questions. Okay, so you see the top producer, it's produced in billions of tons. So the top producer is China, and of course India also produces a lot of steel, and the top company is ArcelorMittal, followed by so many other companies. But the key news here is the magnitude, the amount of steel that is getting produced every year. It's a lot, and that brings down to the next important topic, that is the emissions, right? So this is really significant. We are talking about 1.85 ton of carbon dioxide per ton of steel, and we are producing billion tons, and this is translating into 3.7 gigaton of CO2 in a year. Okay, we are talking about really a huge magnitude of emissions. So just once again, to put it in perspective, it's USA, China steel. That's the emission ladder we are talking about. So it's quite a bit of emissions in terms of the numbers. So 7 to 9% of direct emissions from the use of fossil fuels is from the production of steel alone. And a very, very important number here is that if we are going to go towards 1.5 degrees Celsius global mean surface temperatures, the emissions from this production should be cut down to 80% level than it is now. That is asking for a lot. It's you will see how it is not just a snap of a finger where you say, oh, we just recycle steel and then solve this puzzle. It's not easily solvable. Recycling offers real benefits in terms of saving energy as well as in reducing emissions, but that is simply not going to be enough if we are going to stick to 1.5 degrees Celsius GMST. Okay, it's an important slide. Please pay attention. So the first thing is that the steel industrial recycling is a very well established process. Okay, so we have enormous amount of percentage of recycling of steel. We are talking about 85–90% from some sectors, and the target rates of recycling is much higher in the forthcoming years. And in Western Europe already 55% of production of steel is from scrap. And pay attention here. So we have the primary production of steel process, which is called as the BF/BOF route, which is the blast furnace basic oxygen furnace process. And then we have the secondary production, that is the recycling process, which is done in the electric arc furnace. Okay, but scrap is used in both these processes. In EAF, it can be exclusively scrap. So EAF is a traditional secondary recycling process, but the scrap is also used in the primary process as a coolant. Okay, so this is an important complexity that you should understand. And in EAF, sometimes you also have usage of DRI, direct reduced iron, from which steel is made. See, for the traditional BOF route, you have 1,770 kg of carbon dioxide per ton of liquid steel, whereas for the electric arc furnace route, that is the secondary production, you have substantially less CO2 emitting per ton of liquid steel. The same for the BOF in terms of energy consumption. It's 4,900 kilowatt-hour per ton, whereas for EAF, it's quite less. It's just 1,100 kilowatt-hour per ton. So you have very well-established recycling process with very well-defined savings in energy as well as in emissions. Here's something that I wanted to talk to you about. It's from an article in which they wanted to calculate how much kilogram of CO2 in terms of emissions they are saving because of the usage of scrap and because of recycling. And they encountered one complexity and they tried to solve this complexity. And it's quite simple. So for instance, for the BOF route, the basic oxygen furnace route, the LCI, the life cycle inventory for steel production, also includes scrap. Okay. So what they wanted to simply know was that, imagine that if you didn't use any scrap, imagine if it is 100% based on primary metal production without any scrap, with zero scrap input, what would be actually the emissions from that per kilogram of steel? That's the only question they have. So they tried to solve it with multiple different equations, and they tried to come up with the scrap life cycle inventory, and all these terms you could read through. This is something that you already know. So they found it that for the primary production, when you have zero scrap input, you emit 1.92 kilogram of carbon dioxide per kilogram of steel. Okay, and then they finally found out that you save 1.5 kilogram of CO2 emissions, because the other thing is already measured, with 13.4 megajoules of primary energy that you save, which translates into 73, 64, and 90% of savings in emissions, energy, as well as in the reduction of ore use when you compare it with 100% primary production. I already told you in 2 slides before. Why did I bring it up? Because just read through these 2 slides. It's about thinking about a methodology. So they had a problem in hand. They thought, okay, we can have the BOF route and we should be able to calculate how much we save, but how can we know the numbers when the real production doesn't happen with 100% primary input, but they also use scrap. So they had to go from scrap-based input to simulating an input where they don't use scrap and then subtract it to find out how much we do have in savings. That's how you think about a methodology in terms of using the life cycle inventory and to calculate savings in emissions, just to introduce you to a methodology, nothing more. Here we are going to talk about a study in which the focus is on stocks, the steel stocks in the entire Chinese steel cycle, and it talks about the relationship between the role of stocks and the conception of steel circular economy within China and the circular economy package of China. It's very important because China is in the forefront of steel production and they have done material flow analysis, which gives us a sort of scenarios based projection to until the end of the century. So you could understand that it is quite an important thing to look at. So what do we see here? We see here that when they tried to do the prediction in flows in tons per year, you could see that it has a sort of peak after which it normalizes. So what they are predicting in the first place is that there will be a consumption peak right around what 2025, 35, 25 to 30, after which you will have a drop down, and at the end of the century we will be somewhere at 60% of the peak value in terms of consumption. So that's a really important fact. The second thing is they predict that there will be a continuous drop in domestic demand. There are many reasons to it. One of the reasons they postulate is that there will be a decline in their population, and combined with the fact that there could be, let's say, advanced developments in infrastructure, because notice again, steel is primarily, a lot of it is used in construction sector. So this will lead to a drop in the domestic demand. So they analyzed and they wanted to analyze why would such a drop in consumption would happen, and in which areas would it happen, and how would it affect the scenarios in general. And then you have this graph, and you could see it's for construction, machinery, transportation, and all other appliances. Okay, and they find that the drop in consumption is related to the maturing construction stock, because as I told you, you have, let's say, a saturation in consumption because of a lot of infrastructure development already, and then you have the maturing of the construction stock. So one other thing that they find here is that you could see the square is the old scrap supply exceeding the demand from construction, and the circle is the old scrap supply exceeds demand from the machinery. So you could see the old scrap supply exceeds demand from the construction much earlier even. So around 2025 to 2035. So what does this mean? You are going to have a lot of secondary resources coming in. So what does that mean again? You need to have infrastructure to handle such secondary resources. These are already, we are looking at a century scale of predictions here. These are already very important information to know. So what they are saying is that currently they have enormous infrastructure that is geared towards primary production. That's not going to stop soon, but around 2025 to 35, you're going to have a constant supply of old scrap, which means, as you know, end of life scrap that is going to come in, which means you have to think about either expanding secondary production, constructing more and more of EAF based plants, or trying to somehow imbibe these scrap into the current processes and to develop, let's say, more scrap based production. So that's going to be really a challenge, because Only as of now, currently at least, I know the year of this publication, maybe 2015, not so long ago, 9% of the Chinese steel is coming from the secondary production. So if there is going to be enormous supply of these old scrap that is coming, and there is no infrastructure to actually host and process these scraps, they're going to be dumped in the world market in one way or the other. So that's going to be a challenge. And here they postulate three important challenges that is going to be coming forward, and we will see all these three important challenges. So the first challenge is quite interesting to think about. Before we even go to the challenges, it's quite interesting to think about, because these are these challenges which are very particular to steel, and as I have already explained to you, steel is going to play really an important role. So the first challenge is that they are going to face a consumption peak. So the in-use stock is growing at a really enormous rate, and put this together with the fact that the domestic demand is going to decrease. And how do you solve these things? Okay, either you can curb the production capacity extension. So because already there is, let's say, a reasonable expansion of the primary production that's happening now in China. So you have to curb that by somehow, because if you don't curb that, if you encourage that, if there is going to be more and more primary production, imagine that once you have the consumption peak that I showed you, there is going to be a trough. The consumption is going to drop down. So at that point of time, if you have enormous production capacities, which depend on the fact that you have to keep producing, then it's going to oversaturate the market. The steel has to go somewhere beyond, and that's going to be a problem for sustained production. So either you can have, one of the ways to address this is you can curb the production, primary production in some ways. The other way is to think about sustained growth of construction sector. This is what they propose. I don't know how much this is a possibility, but think about it. You have to have infrastructural development in a sustained way to host the steel that they are producing. If it's the scenario that I took for China, it could be similar for many other countries as well, including India. So the second important challenge that they are facing, and the consequence of what is happening right now, is the scrap boom. I already explained to you the scrap boom. The old scrap production is going to increase because, you know, a lot of it has already been used in construction sector, and they are going to reach the end of life, and we are going to have a lot of old scrap. And what they are predicting is that around 2025 to 30, there is going to be a lot of export of old scrap. A lot of old scrap is going to be dumped in the world market. And to solve this, to negate this, they believe that you have to have large scale domestic utilization. So somehow you have to have an expansion of your secondary production and curbing of your primary production, which directly correlates with formulation of a circular economy to deal with both these problems. Imagine the fact that you're going to have a peak in consumption, you're going to have a boom in scrap where you're going to have a lot of waste. So you have to have infrastructural capacities to deal with it. The third problem, which is something that we will deal with a bit more in detail, and it's equally important, is the quality of recycled steel. See, we are going to have steel from so many different sectors, but steel is a complex alloy, and each alloy with different alloying elements serve a particular purpose. Okay, so once you have, let's say, a loop of different alloys joining together, then it is much more difficult to derive value from it, because what you want to ideally have is that if your steel alloy is performing a particular function, you want to close the loop in a sense that you want to take that particular alloy and give it back to that particular function. Do you see what I mean? Otherwise, if you have a group of different steel alloys and all of them are coming together as a waste, then there is almost no purpose to it, because it's very difficult to process it. In olden days, it was easy because it was unanimously or mostly used in some set of applications, but with advanced high strength steel and other kind of steels with a lot of alloying elements used in various different applications, you want to channelize the sort of alloys into different sections. You want to sort them into different factions so that you could form closed loops, multiple different closed loops for different purposes. Okay, so the other issue that we are dealing with is the issue of tramp elements. So already I explained a bit what are tramp elements in the previous slide. So for instance, copper is used in some of the functions, but copper is, let's say, detrimental to the steel recycling process. You don't want copper, but you can tolerate some amount of it, but not a lot of it, because it decreases the alloying property, it reduces the strength, so you have that issue. And copper is not, let's say, recycled, but it is downcycled. It's present in the steel, but it doesn't serve any purpose. So that's the definition of downcycling. So you have the issue of tramp elements as well. So keep in mind these three important challenges. So from here on, we are going to talk a little bit about how steel is recycled. So again, there will not be, let's say, a lot of questions or something from it, but it's for your own curiosity to understand how it actually happens. So before that, you already know that there are a lot of different types of scraps, and all these scraps have different types of impurity contents, and they are classified as such here. So usually it is when you have a lot of wastes from with steel in it, you have the shredder, where you shred all these multiple different products into really small particle sizes, and you collect the dust using a dust collector. And then you have, let's say, typically a magnetic separator, which obviously gives you a ferrous fraction, which is more magnetic, and a non-ferrous fraction. And then you have, this is, let's say, a crude way of seeing it. There are so many different separation processes that are applied to each one of the products in different manners. So you have firstly the sorting and preparation of physical separation, where you have separation from metallic products to non-metallics, and it could be done using multiple different techniques. It's sometimes hand sorted as well, and you have the size reduction, which is used sometimes by a press, and you have shredding and fragmentation. Usually this is done in an enormous scale, and as I explained to you, magnetic separation and eddy current separation. I'll give you a little bit of taste about how eddy current separation works, because I saw it in a plant and it's quite interesting. And you have also the let's say the heavy media separation, which is usually flotation, in which depending on the density, you have separation from non-ferrous metals from the shredder residue, and so many other techniques as well. Sometimes steel is coated with zinc, and you have, let's say, a step of de-zinkification, where you have the de-coating so that you could process the steel easily. So many different steps. So this is just a small visualization for you. An eddy current separation usually works based on the Lenz's law. Conducting material which goes through a magnetic field develops a current, which then generates a magnetic field in the opposite direction of the magnetic field which is originally given. So you see, I have seen it live, so it's very interesting to see this. They first have, let's say, a magnetic separation in which the ferrous metals is taken away. So you have the non-ferrous metal as well as the inert non-conductive, let's say, plastics and other components, right? So you pass it through the eddy current separator, and it works based on the law that I just explained before. So you're going to have a repulsive force for these non-ferrous metals, right? So you can YouTube it from here. I don't know if I gave you the YouTube link. Basically, the aluminum and other stuff flies away, and you could see it flies away in this animation and gets gathered in this box. Then you have the plastics and other stuffs gathering in this box. It's quite a fascinating thing to look at. So the steel recycling is done in an electric arc furnace. It's basically a smelting/melting reaction. You have 3 different electrodes, and then you charge a lot of this scrap, and then you lower these electrodes, and then you pass current to melt your waste. And it's usually a really exothermic reaction. So exothermic meaning that you have production of energy from this reaction, meaning it's a spontaneous reaction. So what happens is that you have formation of a slag during this reaction, which protects the sides of the furnaces. So what is a slag? I'll just give you an example. We are going to see a little bit more into detail about how things work in terms of chemistry. It could be interesting to you, it may not be, but just listen it out. So smelting is a metal operation with phase separation. So you have the production of your metal, or in this case an alloy, you have production of steel, and then a component called as slag. So based on the density, the metal stays down, the slag stays up. But what actually goes inside the slag, and when you melt a waste, how do you make sure something becomes a metal and something becomes a slag? That's an interesting question. So what you want to do is you want to remove the impurities, what's called as the gangue, into an oxide phase, which is the slag. But what is the chemical principle behind slagging something off? It's in the Ellingham diagram. So I know it could be a little bit too much chemistry for some of you, but it's easy. Just listen me out. See, in a lot of metallurgical processes, they do what's called as carbothermic reduction or metallothermic reduction. They use carbon as a reducing agent. So you have ores, you have let's say oxide ores or even sulfide ores, or you have sometimes the wastes which are present in oxide form or in some other form. And typically what you want to do is you want to reduce them. So you want to remove the oxygen so that you could produce the metal, right? And Ellingham is a scientist who came up with this diagram which plots the free energy versus the temperature. So the Gibbs free energy versus the temperature. So the ones at the bottom you could see which are having a lot of negative free energy. So when something is negative in Gibbs free energy, it means the reaction is spontaneous. It means the compound is so stable that it is difficult to, let's say, separate it from the oxide form that is present. So for instance, if you have calcium oxide and aluminum oxides here, right? So it's pretty down, as you can see, it's quite negative, which means that aluminum oxide is a very stable compound and you have to supply enormous energy to reduce it back to aluminum, okay? And the ones at the top are relatively easier. And you see these lines are having positive slopes, right? So which means that there is an equation which says Gibbs free energy is equal to enthalpy minus temperature times the entropy. I have already explained a little bit about entropy as a concept. And when you have positive slopes, which means the entropy is decreasing. So as you could see, you have an oxygen molecule here, which is going into an oxide. So a gas going into a solid form. You could already understand this means the entropy is shrinking. So positive slope means you have negative entropy, and negative slopes is for this one particular line, and this is without any exaggeration one of the most important lines in metallurgy. So you have the carbon plus oxygen giving you the carbon monoxide, and this is a line which gives you the interaction point of these lines with various different metal oxides, gives you the point, mostly the temperature at which carbon can reduce these oxides back into metals. So using carbon to reduce these oxides back into metals is very important in metallurgy. So when you want to do this, when you want to reduce an oxide with carbon, you could do it in two ways, right? So you could either, let's say, apply a vacuum and then suck something off so that you drive the reaction to the right, or you could solubilize this metal in some other metal and then drive the reaction to the right. So if you want to increase the formation of metal, there are two different ways. So why is something slagged off? Why is something formed as a metal? That's all inside the diagram. When something has the tendency to be more of an oxide, when the oxide is very stable. So this is a place where the oxides are very stable, not the metal. So only after having a huge increase in temperature or with carbon, you can produce back the metal. So we have components here, and iron is mostly somewhere around here. The components which are more stable are going to go into the oxide phase because they prefer to form these oxide phases, whereas iron can form the metal. So that's the chemical basis of the EAF steelmaking. Okay, so I'm not going to go a lot into the chemical details. It's suffice to say that you have phosphorus, silicon, manganese, and all these things going into the slag phase by reaction with the oxygen. So the oxygen diffusion is really the rate determining step, and to encourage this slagging. So because you want this slagging, because it's sort of this enhancing, kinetic enhancing step. So they use slag inducers or slag formers so that you can have the removal of the gangue material and the enhancing kinetics of this reaction. So let's get into the issue of tramp elements. I hope you understood how the EAF works, the electric arc furnace works. Basically, it's a smelting reaction in which you have the scrap melted into formation of iron, but you want to remove the impurities so that you slag them off to an oxide phase. And what forms and what goes into an oxide phase is dictated by chemistry, and that is shown in the Ellingham diagram. So this is, as let's say, in a very simplified manner that I could put it. Okay, so this is an important slide. This is something very relevant to circular economy, to steel making, and to recycling, the issue of tramp elements. Because of the fact that we are using so many of these alloying elements, we have the vanadium, the chromium, aluminum, silicon, and tungsten, and all of these are alloyed with steel for many specific purposes, and I can go on about the applications, but you could easily Google them. The issue is you are going to have the collection of steel from so many different places, right? And you are not going to have a great level of sorting already because the steel is collected as products from so many different places. How are we going to deal with this issue of tramp elements? Because we are not going to produce one alloy of steel with so many different inputs. You can have, let's say, an automated sorting or a sort of robotic sorting based on infrared or other techniques where it says that this is an alloying element present, so let's take it down to this side and let's pass the other steel forward. That's a possible way, but it's a complex issue to solve. And when you want to have successful recycling of steel, it means that you have to have a strategy to deal with the tramp elements. So how do we do it? Not so very carefully, not so easy. You have multiple ways to deal with it. You can have, as I told you, a dezincification process to remove zinc. And at the lowest end, see, this is a graph between qualitative, between the energy and cost and the effectiveness. So the more you go towards effectiveness in the strategy, that is how much you can remove the impurity in this scale, you also go up in cost. So as a recycler, it's a simple strategy. If you are a recycler, you have two options. Spend a lot of money to get a great quality, or don't spend a lot of money and end up with lower quality. And how much it is going to be acceptable, it's purely a compromise between so many different factors. So you have, let's say, the initial very low effective step of hand picking and shredding. It doesn't give you a lot of separation and the copper concentration is high. And you can go to little bit higher magnetic separation to do it again, or to do manual disassembly. You can, let's say, create cryogenic shredding, which is a topic altogether, or you can have, let's say, chlorination of these things, and just some of these tramp elements can be selectively extracted using chlorine. So they can be chlorinated away, they can be sulfided away. These are ways, but again, these are at the higher end of the energy and cost. So it's a tricky thing. So the suggestion from some end, including from Professor Markus Reuter and other people on environmental panel, is that we could live with impurities. At some point of time, we should say Okay, this is copper, it's going to stay there, it's high, it's going to impact your alloy properties, but that's about it, because we are going to spend a lot more money to remove it than to compromise on the property. You could have many different ideas to have, let's say, a monitoring camera or a qualitative chemical analysis at the beginning stage to have this robotic sorting. It's all going to depend and be dictated by the purpose that it is serving. But at the end of the day, what I want to emphasize is that you have to clearly understand what the issue of tramp elements is and what tramp elements are and how it is going to affect the recycling of steel and eventually the circular economy of steel. Okay. Okay. So until now, I presented you various different aspects of steel, and the next couple of slides are, let's say, a little bit uh, bonkers. It's really out of the focus of even what I'm dealing with in regards to recycling or circular economy. So if you switch off the slides here and then say you can end with the presentation here, feel free to, because it's never going to be asked in exams. But if you're curious about what could be the alternatives to steel recycling, because even with recycling we are going to struggle in meeting the climate targets, continue on. There are two different strategies that is proposed. One is ULCOS. ULCOS is a project I think commissioned in 2007, or the results came out in 2007 from European Union. European Union found about the problem of CO2 emissions from steel long back. Everybody knew it, so they had various different strategies to address it. So many. They had creation of what's called as high SARNA, alternative to BF-BOF route. But one of the important strategies and what they call as a really radical solution is that you could do the production of iron, the metal that's produced at really high temperature in blast furnace with so much of emissions, without any emissions at room temperature using electrolysis. Okay, so that's one solution they came up with. They just took the ore and they dissolved it in a really highly alkaline solution, and they passed current, and they split water into oxygen in one electrode, and they deposited iron as metal in another electrode, and they tried to solve this issue. Sounds simple, exciting, a lot of chemical issues remain. It's not followed up very well, I would say. Here and there people are researching, but it was dropped. But it was an important solution. Much more important, and something that is already being commercialized as we speak, I think they are having $50 million investment, is the molten oxide electrolysis route by Professor Donald Saraway from MIT. It's very interesting. This paper got published in Nature, and usually many different articles do get published in Nature. It's a highly ranked journal, but not from extractive metallurgy field, not often, maybe once in a decade. So it's sort of once in a decade kind of invention. What did they find? They found that you can take these molten oxides, the oxides, ores from the nature, and you can just form the metal by passing current at really high temperatures without any CO2 emissions. And that's a really tricky point, because thus far they have used carbon as an electrode and you have CO2 emissions. So how do you use an electrode that is inert without any CO2 emissions was the challenge they had, because iron melts it. The oxides you have to dissolve and melt it right about 1565 degrees Celsius. An electrode should withstand such huge temperatures, and that's where they had to innovate a lot, and they came up with such kind of innovation. They found a chromium iron alloy, and this was the anode that they produced, a stable anode, inert anode without CO2 emissions. And you could see after the electrolysis, it looks bad, I agree, but it is structurally intact, which is huge in these temperatures. Okay, so they formed a company called as Boston Metal, and it's right now operational, and they're trying to produce iron and in fact steel and so many ferrochrome alloys from these molten oxide electrolysis methods. I am really, let's say, generalizing it a lot. It's chemically quite complex, but it's very fascinating these two routes, Ulcos and the molten oxide electrolysis, both incidentally invented by a scientist called Antoine Alanor, who is in MIT, are really game changers, because they CO2 emission is still even from steel recycling. It's not. It's less than primary production, but it isn't absent, and it's still taxing. And these two methods completely avoid it, and they can formulate a circular economy in a much more robust manner. So often not discussed, but equally or more important. So I encourage you to read these articles and to see about how these alternative methods are also being tried in the labs and sometimes in reality. So having said these things, I think the recycling module is almost as good as ended, but I would like to talk more about battery recycling because it's quite important. And also I'll give you a touch of hint on waste electrical and electronic equipments and how it's recycled. They'll be very short videos, 10-15 minutes each, but there will be a lot of chemistry, but you won't be quizzed on the chemistry. Just understand the salience of these things. That would be enough. So happy Easter holidays, and we will meet after the lectures for the modules on criticisms to CE, as well as the module on legislation and policies. And as I told you, please send me your topics on CBMs as soon as possible within the deadline, so that I can have a list of speakers for the presentation for next month that we have scheduled. So see you then.